Hi everyone. So, my name is Michael, and I will talk about what NuCypher is doing, which can be summarized as privacy-preserving data manipulation in decentralized systems. And also, instead of asking the quiz question at the very end, I will actually ask it in the middle. And it will be a tricky one. So, anyway, well, first of all, what do we mean by privacy-preserving data manipulation? Well, what data manipulation is pretty simple stuff, which is, well, probably everyone understands it as, like, let's say when you do transactions on open ledgers, it's certainly data manipulation, like you subtract some value somewhere and add it somewhere else. Maybe, well, data sharing, we also consider that data manipulation, like you show your data to somebody who is not you. So access control is data manipulation. And also, like doing database queries or doing machine learning is also can be considered data manipulation. Well, preserving privacy is a totally different beast. Well, basically, you want only yourself and the recipient of the data or the result to see the actual data, and you don't want anyone who is not supposed to see what's going on. Well, the question is how to bring these two worlds together. So the first thing that NuCypher focuses on is how to do privacy-preserving data sharing. And then I will tell a little bit about how we can go beyond just data sharing, and then show a little demo of the current status of our NuCypher network, or maybe as of like a month ago, because we're actually close to test that. Anyway, well, first of all, as I mentioned, we are doing decentralized access control, and that will be like what the first thing the NuCypher network will be doing. And we're using something called Proxy Re-Encryption for that. So, well, anyway, what's the problem? Why do we need anything special to do access control in decentralized systems? First of all, imagine how traditional public key encryption works. How would you, well, in traditional public key encryption, you can encrypt with somebody's public key, and then he can decrypt with his private key. Now imagine you have some data encrypted for you, and I don't know, stored somewhere, and now you want to share this data, to allow access to this data to some people. So Alice wants to share data with Bob and Charlie. And normally, if you have public key encryption and you have this data encrypted, you probably want to first decrypt it and then encrypt with Bob's and Charlie's public keys. And, well, can this preserve privacy? Actually, yes, it can, if this all happens on Alice's side. So, if Alice decrypts her own data, if the data was encrypted and encrypts with Bob's and Charlie's public keys, it works pretty well. But you know, what's the problem here is that imagine this application is has tens of thousands of users. Maybe it's a group chat application, and the data is like every single message. And then Alice would have a pretty hard time to encrypt every single message for every single person. And then a new person comes and wants to see all the messages, and Alice wants to encrypt all the old messages for that person again. So that's kind of doesn't scale very well. What happens in the current world? How do we scale this? Well, in the current world, we do all of this on a centralized server. So every participant establishes secure connections with some server on, say, AWS, and the server sees everything in plain, but all the data is encrypted as it's coming and encrypted as it's coming out with everyone's key. Well, this works, but of course we heavily trust the central server to some degree. And this comes with downsides because there could be some hackers or state actors who can look at the data while the data is unencrypted on the central server. And if we go to decentralized world, well, first of all, why would we need to go to decentralized world? Probably we want to get like all the goodness which is given by decentralization, such as censorship resistance, for example. So let's say you don't want your application to be banned from operating. So you want a bunch of complete strangers to run your application, and then actually nobody can control these strangers. So if you ban a few of them, it still works. Well, it comes with the downside. The complete strangers would be actually reading your data. So if you had them unencrypting the data, then they could see everything, and you don't know who they are. They are not even Amazon, they are just, who knows who they are. So, well, you cannot, in decentralized networks, you cannot afford to have data unencrypted on the server side at all. And so how do we solve this problem? Well, something we use for that, to solve this, is proxy re-encryption. And let me explain some video explainer, which I will talk through what's happening, how proxy re-encryption works. So basically, imagine, well, Alice has some data, and she has her key pair, so she encrypts her data, and let's say she stored the data somewhere, and now let's say Bob wants to read this data. So Bob tries to decrypt this data with his private key. He obviously fails because private key cannot decrypt Alice's data, encrypted Alice's key. But what what Alice does right now, she takes Bob's public key, her private key, and calculates something called re-encryption key. So re-encryption key is something which cannot be decomposed into Bob's and Alice's key. It's just like one thing, it's a function of two. But what it can do, let's say if you have a third party, let's call this third party Ursula. If this third party takes this re-encryption key, and data which was encrypted for Alice, Ursula can transform this data to be encrypted for Bob using this re-encryption key. And Ursula is actually a node in our network which can take, let's say, ethers and NuCypher tokens for that. And now she transformed this data into encrypted for Bob, and now Bob can open this data using his private key. So just say it again, let's say Ursula is a middleman who does not decrypt the data, but she transforms from being encrypted for Alice into being encrypted for Bob. And that's exactly what this central server who was decrypting the data was doing. But now this is happening without decrypting the data. So now it can happen in a decentralized way without compromising the data. Well, it's not exactly enough, because let's say you asked one central server to hold this re-encryption key and transform your data. Still, somebody could prevent it from doing that. Let's say this server is located in, I don't know, some politically unstable place, and the government of that place just banned it from operating. Then it cannot re-encrypt anymore, and well, the re-encryption is not happening. That's obviously not great. And in order to fix that, we actually developed something called threshold proxy re-encryption. So let's say you can split your re-encryption key into n pieces, and make it so that only n pieces are enough to actually re-encrypt the data. So let's say m out of n proxies transform the data, and then the resulting ciphertexts are combined by both, and then both can decrypt those. So, and that's actually what we use to build our re-encryption network. So imagine everyone can run a node, and then let's say if I want to share data with someone, I choose n random nodes in this decentralized network, and these nodes get my re-encryption keys, and then the recipient asks those nodes to transform the data here. Well, and everyone can join this network just like, I don't know, joining BitTorrent. And now I have a question, if someone was thinking through what I was talking about. If we build the network this way, that everyone can join, and then I can give these re-encryption keys to transform the data to random nodes in this absolutely free-to-join network, what will be the problem with this approach? How? Yeah.
Preventing the Ursula from reading it.
Yeah, I mean, Ursula will not be able to read because she's doing the re-encryption, right?
Which is data key. They have the key and the data, so they have the key and the data, so they can.
So yeah, can you elaborate, like how did the Ursula have both key and the data?
She has the cipher data and the re-encryption. So what prevents her from reading the data before it sends it out?
Oh, no. If Ursula has ciphertext and re-encryption key, she can see only two things: data which was encrypted for Alice and data which was encrypted for Bob. But the data is being transformed by Ursula inside without decrypting. That's what re-encryption key allows you to do.
You have a civil attack on the network, right?
Yeah, exactly. That's it. So if you have a network which is free to join, then somebody could spin up let's say 1 million nodes, and then if you randomly choose nodes, you probably will choose the nodes of the attacker. So this is the correct answer.
Thank you.
Yeah. We prevent civil attacks by not having like nodes who absolutely freely join the network, but nodes actually have to stake our token, NuCypher token. And token is some resource which you need to obtain. Let's say you probably need to buy it, for example. So you cannot really obtain two huge chunk of the network at once. Then Ursulas are selected with a probability proportional to the amount of token they stake. And also, if they do something wrong, they get slashed. So they lose some of the tokens if they, let's say, try to return garbage to bombs or try to censor some bombs. So yeah. Well, and so how would that be useful? What would be the use cases for this kind of decentralized access control? Well, you can imagine simply sharing encrypted files with multiple recipients, and that's already useful. For example, you can share your medical data, and in fact, most of our early users seem to be from medical data space. Another application you can imagine is something I already mentioned briefly. It's, let's say, decentralized end-to-end encrypted chats. You could be able to share not only every message with members in the group, but also the history. So let's say if somebody joins this group, you can either share like all history or like history before a certain date or whatever you like. Or you can imagine an application such as decentralized streaming. If you had, let's say, if you had some service which some middleman who decrypts data and encrypts for every recipient, then this recipient would be able to see the stream, so probably resell it or something, but you can have this whole service operating in end-to-end encrypted ways, so that there is no one except producer and all the consumers of the video receive it. Well, and these are some of the early users of NuCypher network. Starts integrating as soon as we run up on testnet. Well, that was all about end-to-end data sharing. And we've been often asked if we can go beyond sharing. For example, if we can enable end-to-end encrypted smart contracts. So we started doing some research on fully homomorphic encryption to allow some of these use cases we've been asked about. So what fully homomorphic encryption is, it's just some form of encryption which allows to apply arbitrary computations over encrypted data. So you can run some program over encrypted data, get encrypted output, and actually when you decrypt it, you will see the same thing as if you ran this program over like plain text data. And this is not the only thing to do that, not the only way to do it. I think there are, like, you could use trusted execution environments for that, but then of course it's not as secure because you could have like hardware side channel attacks and so on. Another way is doing something called multi-parser computation, where a bunch of nodes do the computation and talk to each other, and let's say only you can distribute trust to do the computation between the nodes, so they don't know what they're computing. But that approach actually involves a lot of data exchange, and also it's if the nodes collude, they can actually decrypt all the data. So that's why we decided to look at fully homomorphic encryption. And fully homomorphic encryption was believed to be pretty slow. So the fastest we saw before we looked at it was doing like 50, maybe 70 operations per second. And apparently it was possible to accelerate that using GPUs. And we got like 100 times acceleration compared to what we saw. So it's now we're at about 7,000 operations per second for fully homomorphic encryption. But of course now we need to think how to properly apply it to the use case and everything. And anyway, so this was like a short description of what we're doing, and I probably want to show a little demo of NuCypher network, as at least it was probably a month ago. Right now it's a little bit further towards testnet, but since it's in development, I'm showing kind of month-old stuff. So anyway, I'm just going to run, I don't know, probably 3 NuCypher nodes, and then try to re-encrypt Finnegan's Wake book line by line using that little network. So just do that. So I'm first of all I'm running. Well, let's say I'll. Example directory, and I have this let's see, script which runs the node in federated way, well, on this laptop, and I run it at port 4001. I distinguish the nodes by ports because they run on the same machine, and it works, but it can't find any more nodes in this network because there are no more nodes yet. So, and then I'll run a couple more nodes. Okay, that will work. Right, so basically I'm running rich environment in just Decentralized to run the same node, the same kind of node, but on different ports. I'm running second node. And the third node. And actually, looks like nodes found each other, so they know about each other, and have a very small network of 3 nodes up. And now I want to run the actual script, which feeds data to the re-encryption. So just make it a little bit more readable, because the letters are too small. So, and well, basically, the demo which I'm running, so the demo, this is actually the code of the demo which I'm running, and well, probably well, but anyway, what this demo is, it's basically 3 things combined in one demo. So it's like 3 nodes coded up, the client node for Alice, client node for Bob, and client node for data source, someone who encrypts data for Alice. And you don't have to do that all the time, but it's actually interesting that you can fairly easily, just using NuCypher libraries, code up your own nodes if you want to. So, and this is what's done here. So, and now I'm running this demo, taking Finnegan's Wake book as an input, and using, let's say, the second node to start traversing the network flow. And it's, yeah, so, and right now it deployed all the re-encryption keys to the nodes, and using 2 nodes out of 3 to re-encrypt the data. And data is printed by Bob. And you can see that nodes show in the logs that re-encryption is happening. Actually, in the real network, the node will not log out who is re-encrypting for who, because this information can be considered semi-sensitive. Like even if people are identified by IDs, that can be used by, well, nodes can be data subpoenaed, and probably they don't really want to store this information. So this is only happening in debug mode. But yeah, that's the demo of the network. But network is actually much further away from this stage right now, and we are firstly we will run the testnet maybe by DevCon and in a federated regime, and then pretty quickly introduce the blockchain layer, where actually there will be no Sybil attacks possible. Yeah, so that was it, and feel free to ask questions.
Is there a performance over there of the proxy re-encryption?